Okay, let's talk about RC circuits. Recording. I already did this lecture, but I realized I forgot to turn on the recording button, so take two. So what we're dealing with, these are non-steady state circuits. In other words, the current is changing. As a result, you're going to see in a lot of the graphs and things lowercase I. Lowercase I usually means a changing current. Capital I usually means a constant current. It's not hard and fast that way, but that's often what it means. So the idea here is we've got a battery, a resistor, and a capacitor in the same circuit. When we first close the switch, the capacitor acts like a wire. Okay, you can ignore the capacitor when you first close the switch. That means the current through here is just going to be the voltage on the battery divided by the resistor. But over time, charge is going to collect, and then after a long time, there's no current flowing. So a capacitor, after a long time, acts like an open switch. Remember that. That's the key to this whole thing. Initially, capacitor acts like a wire. At the end, after a long time, then the capacitor acts like an open switch. Okay, that's the whole idea. And so, if this is the charge on the capacitor, and this is Q max, right, the maximum charge that could be on the capacitor, given by the capacitance times the voltage, the potential of the battery, right, the EMF. This goes up like this. Initially, 0, when you first close the switch, and the capacitor is charging up. And then that's what happens. As a result, also, the potential difference across the capacitor goes up and approaches as an asymptote, not that kind of volt, V, the voltage on the battery, or the EMF. You'll see it that way sometimes as well. The current, the initial current, I naught, given by the EMF of the battery divided by the resistor, goes like this. And it approaches 0 asymptotically, right? And the potential difference across the resistor, given by the EMF of the battery, also gets to be less and less as time goes on. So this is what the graphs look like. This should look familiar. This looks like e to the negative t, some time constant kind of thing, right? Like drag. So now looking at this circuit, if this is uncharged and the current or this switch is switched to A, then this is going to charge up, right? So initially, the current is going this way. It goes around. And you get positive charge collecting here, negative charge collecting here. Right? Also on the resistor, this is going to be the positive side, right, and the negative side, so the potential drops as you go across this resistor when the current is flowing that way. But when you have it closed today for a long time, then this gets charged up. Right? And so as this is charging, by the way, we need to keep in mind Kirchhoff's loop rule. And the loop rule tells us that so the EMF on the battery is going to be equal to the voltage on the resistor, which is going to be I times R, right, plus the voltage on the battery, or on the capacitor, which is going to be Q over C. Notice lowercase q because Q's potentially changing. I is Q over T, so R times Q over T plus Q over C, or dq dt here. Right. And so then over time, this gets to be 0, and then all the potential difference is across the capacitor. That'll be Q over C. Okay, then though, once this is all charged up, if we turn the switch now to B instead, what we have here is the capacitor acting like a battery. All the positive charge here wants to go away, the negative charge wants to go away, and so now I end up with current going this way. Right. And now in this case, the potential difference across this has to be equal to the potential difference across here. So notice now I've got positive and negative. The potential difference on the resistor switches direction. And so now going across it this way, R times dq dt, R times the current, is equal to Q over C, the charge on the capacitor divided by the capacitance. Right? So this is the voltage on the resistor is equal to the potential difference on the capacitor as it's discharging. Right? And so the discharging works the same way with those types of graphs. Right? So as it's charging, now we can see what those equations are. And so let's fill in QT, Q is a function of time, is given by CE. So this is the charge on the capacitor. CE, C times the EMF on the battery, represents the maximum charge. And so then, and this is approaching that asymptote, right? So this is going to be 1 minus e to the negative t over tau c. Tau is the time constant, right? And so that's what that is. And it's in the next slide. Tau is equal to R times C. That's just the resistance of the resistor times the capacitance of the capacitor. That's it. I is a function of time. The current is a function of time. The initial maximum current is just going to be the EMF divided by the resistor. Right? EMF divided by the resistance. And then this one is decreasing. So that's times e to the negative t over tau. The format for all of these equations is really the same. If it's increasing and reaching an asymptote, what you do is you put here in front what that asymptote is. Q max, V max, the EMF of the battery, something like that, times 1 minus e to the negative t over tau. If it's something that's decreasing, then this coefficient in front is just, the starting point. In this case, that maximum current given by the EMF of the battery divided by the resistor times e to the negative t over tau. They're all the exact same form. Just some coefficient given by the maximum, either the starting point or the asymptote, times either this or this, depending on whether it's going up or down. Right? They're all that same way. And so then the voltage on the capacitor as a function of time is going to be given by the EMF. That's the maximum voltage that the capacitor will have after a period of time, the EMF of the battery. And it's approaching that asymptotically, so it's 1 minus e to the negative t over tau. Okay, that's it. And so this should look familiar from this form of the equation from drag, right? And so we've got, if this is Q max right here, the idea is that after one time constant, so here tau, which is equal to RC, then it reaches 0.63 of Q max. So in one time constant, if something is going up, it reaches 63% of that maximum value in one time constant. For the voltage on the capacitor, this is the EMF, so that's what it's approaching. Then, after one time constant, also, it's at 63% of that maximum value after one time constant. Right? But if it's something that's decreasing, something like the current, right, given initially by the EMF over the resistor, and it's decreasing, then after one time constant, it's at 0.37 of that maximum value. It's at 37% after one time constant. And the same thing is true for the voltage on the resistor. Right. Starts off with the EMF of the battery, but then after one time constant, it's at 37% of the EMF. Okay. Discharging is similar. Right. So here's charging, except now we just switch. So now the current is decreasing if it's discharging. So if the current is decreasing, now it's Q is a function of time. It's going to be capacitance times the EMF times e to the negative t over tau. All right, the current also will be decreasing, so this is I as a function of time. Right? Imagine it'll be high current at first, but then as it continues to discharge, it all just goes away. So this is the initial in the EMF. So C, this is given by Q naught. Right, so we could say this Q naught, e to the negative t over tau. Here it's the lowercase q. The voltage, again, is given by Q naught over C, and that's over R, right? V over R would give you the current, e to the negative t over tau. And then the last thing we're looking at is the voltage on the capacitor as a function of time, and that would be Q naught over C. This also is decreasing, e to the negative t over tau. This might not be in the packet, but it should be there. Okay. Well, this might not be there because in the packet it's this. Q is a function of time, so it's this function divided by C. Right. All right, so let's take a look at some examples. So here we've got, it's uncharged, this capacitor, and we've got a switch here, so I need to do this. That's the switch. And so first thing is draw the circuit, calculate the time constant. Right, the time constant, tau equals RC, so that's just 3 times 10 to the 6th, 3 mega ohms, times 0.1 times 10 to the negative 6. And so this gives me 0.3 seconds. Okay, so that's the time constant. Now I want to know the charge on the capacitor and the current through the resistor at these various times. The first one is after one time constant. So 1 is actually really easy. The charge on the capacitor, Q, so let's write it this way. Q at 3.3 seconds, that's after one time constant, is going to be 0.67 times the maximum charge that can be on here, given by the EMF times this, right? So it's 45 volts times 0.1 microfarads. And I think the answer turns out to be 284 microcoulombs. The charge after one time constant will be, this will be 63%. Sorry about that. And this will be 0.37. And the current, the maximum current is going to be given by V over R. Right, so 45 volts over 3 times 10 to the 6th ohms. I think that should come out to about 5.52 microamps. Right, so that's 1. For 2, now this is after 2 time constants, and we don't have a special percentage that we can just remember for that. So let me put these over here. 2. Charge as a function of time is given by, and charge is increasing, right? So this is going to be the EMF times the capacitance. So let me just write that. That's the maximum charge rate, Q equals CV. And since it's approaching an asymptote, it takes this form. 1 minus e to the negative t over tau. And so for this, all we're doing is we're plugging in 45 volts. This is 1 microfarad. This is the 0.3. And honestly, I don't have the number written down, but as long as you plug the numbers in the right way, the form of the equation is the important thing. And then the current as a function of time will be given by the EMF over the resistor. And since this is decreasing, that takes the form e to the negative t over tau. Okay. Okay, and then 3, all you're doing is plugging in into here 1.5, right? And for number 2, you're putting in 0.6 as time. Okay, and now for example 2, here's our circuit. Here's how we calculate the time constant, which is part B. The switch is now closed. So if we close the switch, calculate the maximum charge on the capacitor. So 1, Q max is C times V, or C times the EMF of the battery. So that's going to be 12 times 5 times 10 to the negative 6. So that's going to be 600 microcoulombs. And then also 2 now is the maximum current through the resistor. So 2 I max is going to be the EMF over the resistance. So that's 12 volts divided by 0.85 mega ohms. And that'll be about 14.1 microamps. Right? Now this is good. We found these. These are going to be our coefficients in our equations, right? And so then for 3 it says charge is a function of time. Right? So charge is a function of time. Charge is something that's decreasing. So we start with our, charge, what am I doing? Would be Q. Q is something that's increasing, right? And so that's the charge collecting on the capacitor. So that's going to be this, 600 microcoulombs times 1 minus e to the negative t over 4.25, which is the time constant. And then 4 is asking for current as a function of time. 3, 4. Current as a function of time is going to be this, 14.1 microamps. This is something decreasing, so e to the negative t over tau, where tau is 4.25. And those are our functions. The charge on the capacitor after 1 time constant, you take this, and after 1 time constant, the charge is 63%. So you just find 63% of 600. And well, I have that number. It's 0.378 microcoulombs, which doesn't really make much sense, because that does not look like 63% of that. Let's see. It's got to just be 378 microcoulombs. Maybe it was 0.378 nanocoulombs. And then the current is going to be 37% of that after 1 time constant, which is, I think, about 5.22 microamps. Now we want the graphs. So the graph of Q versus T charge looks like this. Okay, and this, Q max, is 600 microcoulombs. Okay, and then the current as a function of time is going to be decreasing, and this starts off at 14.1 microamps. Okay, so that's example 2. In example 3, we have a capacitor discharging through resistor R. And so we want to know after how many time constants will the charge be 1/4 of its original value. All right, so we've got Q equals Q naught e to the negative t over tau. All right, it's discharging, so the charge is decreasing. We've got this. I want to know when this is going to be 1/4 of this. So 1/4 Q naught equals Q naught e to the negative t over tau. Q naught cancels out. I'm looking for t in terms of tau. So now I've got natural log of 1/4 is negative t over tau. T then is negative tau times natural log of 1/4. Right? So after negative natural log of 1/4 time, that's how many time constants will be when it'll be at 1/4 of the maximum charge. How about the stored, the energy, the stored energy? So remember, U is 1/2 QV, right? And so Q will be given by this function, Q naught e to the negative t over tau. It's discharging, right? Times, and then V max, the voltage will be given by V max, or the original voltage. That also is decreasing e to the negative t over tau. Okay. Now we can combine this. We get 1/2 Q naught V naught, the initial, or V max, e to the negative 2t over tau. Okay. And so this, by the way, is U max also, right? And so now I'm going to set this, so 1/4 of U max is 1/2 of U max e to the negative 2t over tau. Okay. Rather, this is U max right here. So it's like this. Okay. Thought that was kind of funny. And now I end up doing the same thing. So natural log of 1/4 is negative 2t over tau. So t is negative tau over 2 times natural log of 1/4. Okay. And so then how many times, after how many time constants will the current be 1/4 of its original value? Again, this ends up looking just like this one right here, except this is I naught instead of Q, and it ends up being exactly the same because I naught Q, because current is also decreasing. Current always decreases, charging or discharging. Okay, so in this problem, we've got 100 volts on the capacitor, and then we connect it to the voltmeter, and then it starts to drop, right? Why? Because current is going to go through the voltmeter, and we're going to lose charge, and therefore potential difference on the capacitor. And it looks like this. After 6 seconds, it's half of its original value. And so here's our, voltage as a function of time is V naught e to the negative t over tau. Right. And so this is 1/2 V naught e to the negative t over tau, because I know what this time is. I know the time is 6 seconds, and this is 50%. So this cancels out, and now I end up with the same kind of thing I had before, right? Negative tau times natural log of 1/2 equals t. Except here I'm going to be solving for tau, because if I can get tau, then I can get RC, right? So RC equals negative t over natural log of 1/2. Right, I divide and then the negative there. And so then t is 0.6, or rather 6. Right, so this is negative 6 over natural log of 1/2. And I think that turns out to be, well, I don't know, because now we're going to set this equal to c. So c is negative 6 over the resistor, which they tell us is 10 mega ohms. Natural log of 0.5, and it comes out to 8.65 times 10 to the negative 7th farads, right? And so then we want to know after how long after the initial connection will the meter read 25 volts. So that's when we're getting down to 1/4. So this is 1/4 of V naught equals V naught e to the negative t over tau. Now we can figure out what tau is, because we have R and we have C. So now when we solve this for t, again we're going to end up with t is negative tau, natural log of 1/4. So tau is this times the 10 mega ohms. And then I multiply by natural log of 1/4, and it comes out to be about 12 seconds. In example 5, we've got the capacitor. It's got 800 volts on it, and then it's discharged through a 25 kilo ohm resistor. We want to know the total energy that's lost. Well, really all of the energy that's lost. So we look at all the energy that's there, and however much energy is in the capacitor, that's how much is lost due to joule heating. And so my formula, what do I know? I know capacitance and I know voltage. So I can put this in terms of the capacitance and voltage, and I'm good. So it's 1/2 CV squared, right? And so I just plug in my numbers here. So C is 5 microfarads, and the voltage is 800 volts. Square that. I think you get 1.6 joules. Right? That's how much is lost. For example 6, we've got the voltage on the capacitor and the voltage on the resistor both on the same graph. And really this should meet halfway. This should be 0.5 of the EMF. So it's a little off. I'm not a great artist. So we're looking for the place here where when VC is equal to VR, right? The voltage on the capacitor is equal to the voltage on the resistor. Well, this is something that's increasing. So this is EMF times 1 minus e to the negative t over tau equal to, when the EMF on the resistor, that's the EMF, this is decreasing, so e to the negative t over tau. Right? So this cancels out. I'm left with 1 minus e to the negative t over tau equals negative, or e to the negative t over tau. So I get 1 equals 2 e to the negative t over tau, because I add that to the other side. So 1/2 is e to the negative t over tau. So I'm just going to get this in terms of tau. Right? So it's going to be negative tau times the natural log of 1/2 is t. So it's going to be something like 0.693 tau. Right, so 0.693 times the time constant, that's the time at which VR is equal to VC. And that's it for day 1.